Hi, can you hear me? Just a minute, I'm connecting my audio. Can you confirm if you can hear me? I'm not sure. Okay, can you confirm if you can hear me now?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, we'll start. Sorry for the delay. Okay, so we are meeting after 3 weeks, right? The week, 2 weeks before that was the IOPM exam. And I know that some students have scored well, but not everybody has scored well. Maybe some has scored 40, 30, 20, 10, 0 also. So I thought maybe it's time to give some, pep talk kind of thing to boost your confidence so that you don't stop studying. So, I mean, for those who scored well, of course, you will be happy that, you have done well. For those who did not score that well, don't be sad. I mean, you didn't score because you still got a chance to learn something about, how you think. Like you must have done something right in those 3 hours. It's not like even if you did not get even a single problem, you must have thought something that okay, this is the right approach for this problem. So whatever you did right, be thankful for that you did that right, and then also look at what you can improve. Like what you could have done better. Maybe one thing is that maybe you can manage your time better. Because I from some students I got the feedback that they got the method right, but the calculation mistake they did maybe. So even though their approach was correct, they did not get the marks. So if that is happening, then I mean, in the exam, like what you could have done maybe is that after 2 hours you understand okay, I'm not going to get a lot of problems. So let me ensure that whatever problems are already solved, they are definitely correct. So instead of using the last 1 hour to try to solve more problems, maybe one strategy at that point would be revisit the problems you already solved and double check your calculations so that at least those problems you will not lose marks, something like that. Okay, so there are multiple ways we could have, thought about how you can improve your score in that last 1 hour or something like that. But ultimately, I mean, don't worry so much about it because, as you know, that pre-RMO is a very different kind of exam than other Olympiad where we have no subjective answers. So really, the RMO is where your Olympiad experience truly begins. So don't worry so much about pre-RMO. If not this year, you'll clear it next year. Okay, it's not such a big deal. But I mean, it would have been pointless if we prepare only for pre-RMO, we all clear pre-RMO, but we are completely unprepared for RMO. Then that is useless, right? Because then we are not going to get the benefit of that. So that's why we'll continue to keep preparing for RMO as what we are doing always. And so, I mean, don't worry about the score and all those things because honestly, uh, you won't remember this score forever. Like 5 years down the line, you won't even remember that, okay, I scored this marks in this exam. It will be just like a past event. So, I mean, right now it may feel like a big deal that you did not score this much or whatever. But sooner or later, that moment will pass and you will forget about it, that something like that will happen. So, but I mean, don't forget about it. And in the sense that don't learn from it and learn whatever you can from that and try to improve yourself. And then we'll keep moving for the next thing. Okay. So, yeah. So don't worry so much about it. I mean, honestly, if it were possible to conduct an exam at such a wide India scale, which is like subjective, like RMO, we would have done that. But at least right now it is not possible. So that is why we have to use some kind of objective exam. And so that comes with some disadvantages that, I mean, you don't get rewarded for your steps or calculation. You only get rewarded for the final answer. But I mean, overall, still, what I would say is that even if the paper is difficult, it will just shift the spectrum. Like whoever is the better student will still remain ahead of the others. So it is just that you're compressing the marks down into a smaller range, like maybe 0 to 20, 30, 40. But your relative ranking doesn't change all that much. Okay. So, so don't worry about that so much. So, how are you going to prepare for RMO that we have the next few weeks for us? And this applies for anybody. Like even if you already know that you don't not have scored many marks, so you may not get cleared for RMO, but it doesn't matter. Okay, you are going to keep studying for that because, as I said, if not this year, next year you are going to require this. So, in fact, on the day of RMO, I want all of us to write the paper. So, regardless of whether you are officially selected or not, we can sit at home and attempt the paper, right? So maybe not during the exam time, but after once the paper is available, you can do that at home. And I would like to, give that a serious attempt. Like that is the real Olympiad, which you want to do well. Okay, so keep that as the objective in your mind. So, given that you don't have lot of time, I thought we should change track a little bit. That so far you have been doing one theory topic and studying all the problems of that one topic. But with that approach, we will not complete all the topics that we are required to learn for RMO in that way. So a different approach can be start from the problems. Okay, we start solving problems, and in the course of that, whatever theory topics we encounter, that these are the things that we have not done, and they can be from any subject, geometry, algebra, combinatorics. So we'll study those topics in the context of that problem. Okay, so it's like a reverse approach. So that is also one effective way to do it, and in fact, that will highlight that how every theorem is a problem-solving tool. That it is not just a theorem like a theoretical result, but how do you convert that into a problem-solving idea? So that is what I would like all of us to emphasize. Okay. So with that in mind, the I think 4 problems which I shared yesterday. So we can start by discussing those. And so every week I'll share a few problems from mostly RMO and maybe sometimes INMO also. I mean some easy INMO problems, not very difficult. And as far as possible, I'll try to use the older RMO problems. The reason is that the recent RMO papers I want to keep intact for you to practice in exam environment. So, like RMO maybe 2012 onwards. So, last 10 years RMO paper, if you are not seeing them already, I would say that attempt them like a exam. Like you like RMO 2013 full paper, 3 hours you can attempt. So, for that reason, I cannot cherry pick problems out of those papers. Okay, so I'll mostly pre 2012 papers I will try to scan and try to pick good questions from that. Okay. So any particular problem you would like to start discussing out of the 4 ones? Which one did you find easiest? Maybe we can start with that one. Did the geometry problem? Okay. And can you raise your hand online if you have solved the geometry question? Okay. So, yeah. So maybe everybody did not get enough time to attempt it. So I'll give you a few minutes to think also, but I'll just construct the basic diagram. And meanwhile, I'll come around and also look at what are the ideas which you have tried. Diagram. Both of you have solved this question. Yes. B and C A D R. Yeah, but three of those subject, right? So that will be A equal to B square. A equal to B square. A is equal to C. Okay, anybody online? Can you tell me? Rohan?
Yes, sir. Sir, so it was also given in the question that BD by DC is equal to BF by AF.
Correct.
And so by basic proportionality theorem, FD is parallel to AC.
Yes, correct.
And also quadrilateral FKDB is cyclic.
Yes, correct.
So angle FBK is equal to angle FDK.
Angle FBK is equal to FDK, correct.
And since FD is parallel to AC, angle FDK is equal to KAC.
Correct.
And so FBK is ABE and KAC is CAD.
Correct. So basic angles is right. So these two angles are equal and these two are equal because this is parallel to the base. Okay. And some variations of this. So for example, what was it? I think you showed triangle FKFB. One more way to show is triangle KFB is similar to triangle DAC, right? This. Okay, and then that also set up the same similar. Any other approaches? Like any completely different approach? If anybody, you can tell me. Okay. Do you know anything else about this point E? it is a midpoint, right? Why? Because of Seva's theorem, maybe. I mean, generally, this is a known fact that if there is a point on the median and you draw the Seva configuration, you get a line parallel to the base and vice versa. So E is also the midpoint of AC. Okay. So I had one approach. Now looking at your approaches, my approach is needlessly complicated, but still to share that how I started to think about what we can do. So what we wanted to prove was this angle is equal to this angle, right? This is the yellow ones which I've shown. And so that to me looked like the tangent secant configuration, right? So if I imagine that it's a circle passing through AKB, right? So I'm interested in this circle AKB. And if that is, I can show that it's tangent over here, then I'm done. And so, I mean, going by power of a point kind of a thing. So I would like to show that EA square is equal to EK into EB. Okay. And so EK into EB looks a lot like the power of a point E with respect to some circle, but it is not particularly convenient, or I mean, how do we show this is not clear. But this is where what I observed was that, so EA, because I already said that E is the midpoint, so EA square is nothing but EA into EC, right? So, I mean, this is equivalent to prove that EA into EC is equal to EK into EB. I have to prove this. Maybe I should draw a question mark here. Okay. And so now, in some sense, this is like the PA into PB kind of a thing, right? So EA into EC is equal to EK into EB. Only problem is that KB are on both on the same side. So how do I fix that? If only K went to the other side, then it will be like the power configuration. So what I did, that if you just extend this, like extend KE to a point L, such that basically I want to complete this parallelogram. There already one pair of midpoints is there, so I'm going to construct one more pair of midpoints, so that this AKCL is a parallelogram. And so what happens is that this EK, right? EK can be replaced by EL now, right? So now on the RHS I have EL into, and this I want to show is equal to EA into EC. And that will follow if ABCL is cyclic, right? So it is enough to prove that ABCL is cyclic. And do you see why that is going to be the case? Because I mean, this we already have one pair of supplementary angles, right? This FBD was supplementary to this angle, and now that same angle is going to be replicated over here, right? So angle ALC, which is equal to angle DKF, is supplementary to angle D. And so therefore these 4 points are cyclic, and there is. Okay. So I mean, there is not much point to doing such a long calculation, except that maybe instead of angle chasing, we are doing some kind of power point chasing. That is the only difference. But yeah, I mean, many other simpler approaches are also there to this question. But it's still useful to think of an alternate approach like this, because it shows some other properties of the configuration, that because of this point E being the midpoint and this parallelogram, that leads to few other possibilities. So, I mean, in particular, do you see what it means is that if I extend the median and let it meet the circumcircle at one more point, I mean, you don't often study this configuration, so let me just redraw the diagram to highlight this fact that, I mean, we have lots of properties about what happens where the angle bisector meets the circumcircle. But the point where the median meets the circumcircle, we don't know much about. We never really paid much attention to that point. So I'm just relabeling the diagram for our convenience. So now let M be the midpoint of this side, and I'm extending it to meet the circumcircle of ABC at some point. Let me not call it L, because we reserve the name L for that midpoint of the arc, right? I'll call it N. Actually, we use N for the 9-point center, but let it be. I don't have a lot of points here. So what this configuration suggests is that if I take this point N and complete this parallelogram, Okay, or in other words, if I take the reflection of this point n over here, then that is going to be the point k of our configuration. And so for this particular point k, if I draw these lines, of course, like again, as usual, this is going to be parallel to the base. But not only that, this is going to be a cyclic quadrilateral. This, the one which is getting formed inside. And so most likely that is the only unique cyclic quadrilateral for this point k. Like if you change the location of this point k, you will not get a cyclic quadrilateral. So that is something interesting that uh, emerges out of this. And I don't, but maybe more properties over this point n, which may be worth exploring. In general, medians and angles don't go very well. Like the angles that the median forms at the base, right? These angles are don't have very nice formulae. Like you can get some trigonometric versions of the formulae, but otherwise they don't have very nice expressions. So yeah. Okay, anything else to share about this problem? Okay, then the next one. So next, which one you want to discuss? Question 2 of the same paper, that A1, A2, A 2011. Have you solved? Anybody? Online? Anybody who has solved that permutation question?
So I got one of approach, but I don't know it's right or wrong.
Okay, we'll give some time for everybody to think. Okay, then I will ask your approach. But just to check, are you using pigeonhole principle in any way? Okay. Okay, so just thinking aloud, I'm not discussing the solution yet, but how do we start thinking about a problem like this? That if possible, let it not be true, whatever they are claiming, then what will happen? So these numbers are there and one. So firstly, yes, Kana.
I found the solution.
Okay, wait. We'll discuss after a few minutes. I just want to motivate the idea first that what are the possible values that this expression can take, right? What is the smallest possible value and what is the largest possible value? So smallest is 0, right? Absolute value. And what is the largest possible value?
2010.
2010, right? Because, I mean, maybe A1 is the smallest possible number, or sorry, A1 is the largest possible number, or something like that. So this belongs to the set, and every number in between can be possible candidate, right? So there are 2011 objects and 2011 numbers. So if no two of them are equal, then what is the only thing that has to happen? Each has to occur once, right? So there is some AI for which this value is equal to 0. For some AI, the value is 1, and so on and so forth. So in some order, all of these items are going to be taken. So if I make a this, right, A1 minus 1, A2 minus 2, A 2011 minus 2011. So this entire list is consisting of 0, 1, 2 up to 2011 in some order. We don't know. And our attempt is to find something wrong with this picture, that for some reason this cannot happen. That is how we are going to claim the contradiction. So what can go wrong is the question, right? And for those who have solved the question, do you see why that number 2011 was chosen? I mean, of course, it was the year of the paper, but that's not only that. If there was some other number in place of 2011, this property may not be true. So there is something special about 2011. Oh, sorry. The last term is 2010, right? Not 2011. So the difficulty is we don't know the order. Which one is first, which one is next. But can we do something with the numbers where the order does not matter? Kanav, can you type the solution in the chat? Then I will take a look.
Okay.
Yes, that is right. Only the first line that the sum has to be even. And you are saying obviously. I mean, in the exam, I would suggest that maybe you can explain that. But I understand that you understand why that is even, right?
Yes.
Okay. So the whole game is about parity. Because the thing about absolute value, there is one very important property about absolute value that we should keep in mind. That because of the absolute value, the magnitude, the sign may change, right? The positive term will become a negative term. But in the process, when you are talking about integers, right, the parity doesn't change, right? Like even if plus 5 becomes minus 5, it is still odd. So if I am going to do everything modulo 2, right, then I can drop the modulus, the absolute value sign. Okay. So in other words, I can say that this like term by term, like ai minus I. So term by term. So a1 minus 1 is congruent to like without the modulus sign. Okay, if the first term is even, then the second term is also even, and vice versa, and so on and so forth for every term, right up to the last. And now, if I add all of these together, what do I expect to happen? Because the numbers are just the permutations of the numbers 1 to 2011, right? So every number is going to occur once as the AI and once in the right column somewhere. So like term by term, every term is going to cancel, right? If I add everything together, I'm going to get 0. And so what it means is that the sum is even. So this original sum, right? This original sum of these AIs, right? That is even. Because when I remove the modulus sign and add it, I get 0. Okay. And we are claiming that these numbers are nothing but the numbers 0 to 2010 in some order. But if I add these numbers, what happens? You get an odd number, right? And the reason why that happens is because 2010 is a multiple of 2, but not of 4. So when you apply that n into n plus 1 by 2 formula, you are going to get an odd number. So this sum is odd and this sum is even, which is a contradiction. Oh, was this your idea also?
Sir, I got this idea, but my approach was the maximum value can achieve is 2010. And we can prove that if we achieve the maximum value, we cannot achieve 2009.
If we achieve maximum value, we cannot achieve 2009. Okay. Why?
So because 2009 only can achieve by 2011 minus 2 and 2010 minus 1.
Yes, correct.
And for achieving 2010, we have to use 2011 and 1.
No, but it could happen on the other direction also, right? I mean, mm, if I let me, I get the general idea, but I'm not sure if it works out. So your claim is that, so if I understand your claim is that if 2010 is achieved, then 2009 cannot be, right?
Yes, sir.
And the reason why we're saying that is so let us find the number of ways in which we can construct 2010 and 2009. So 2010 can be achieved by the only combinations being if A1 is equal to 2011 or if the last term is 1, right? Either of these possibilities is fine to achieve 2010. And for 2009, what are the possibilities? Either the first term can be 2010 or what else can happen? A2 is 2011 or and same from the other direction, right? Or A 2010 is 1 or A 2011 is. So for 2009, all these possibilities are there. So I'm not sure if we are eliminating all of them. Like if let's say 2010 is achieved using this combination, that still leaves the possibility that, for example, this one can happen, right?
Yes, sir.
So actually, the modulus sign causes the problem. Because of the modulus sign, it would be either way.
Okay, yes, sir.
Without the modulus sign, I think what you're saying would have worked out. Because I mean, if you notice what his idea was that if you notice the first two pairs, right, they cannot occur because A1 is already occupied here, so this cannot happen. And 2011 is occupied, so this cannot happen. So the first two get eliminated. But there could be more approaches, like what you are trying to do here. Um, so there is, as I said, now let us use this opportunity to study some theory about permutations, which can be useful in some context. Not related to pigeonhole principle, but about the space of all permutations in general. Okay. So whenever you have n objects, we know that they can be permuted in n factorial ways, right? Well, before that, I hope the solution is clear. Any doubts in that? And also now, so you can see that the number 2011, what was special about it? It was such that the previous term, that n into n plus 1 by 2 thing, is odd. So for every number which has that property, the same argument will work out, right? So I think all the numbers of the form 4k plus 3 and also 4k plus 2, maybe. I think 4k plus 2 also, right? So if any number of this type is there, the same argument will happen. Maybe interesting for us to ask the question for the other two, like if the number is of a type 4k or 4k plus 1, can we construct an example where this property is not satisfied, like where all those ai minus I are distinct? Or if we are able to construct a counter example, then we can be sure that this property is only true for 4k plus 2 and 4k plus 3. Or otherwise, it could be very well the case that for all numbers, something goes wrong. So that is an open question for you to think about. Okay, that can this problem be extended to any natural number or only 4k plus 2 and 4k plus 3? Okay, so think about this at home. And actually, I mean, every problem that you solve, don't just leave it there. Try to see how you can convert that into one more problem, RMO problem or PRMO problem. Even the previous question, I immediately start to think that what we can do. So I already have constructed a problem in my mind that in this diagram, what is the special condition under which K becomes the centroid of the triangle? You see, K already in my diagram is looking very close to the centroid. So there must be some special triangle ABC where K is actually the centroid. And so what is that triangle? Okay, so I mean, every time you see a question, it should lead you to more questions. Okay, so anyway, think about this at home. So coming to some properties about permutations in general. Okay, they are a very interesting object. So permutation. Permutations are really powerful. It is not just like how many ways are there to arrange objects on a straight line. They are they have very deep-reaching consequences in all theory of mathematics actually. Because one, there is a very fundamental theorem called Cayley's theorem or Cauchy's theorem. I forgot the name. But every group is isomorphic to a permutation group. Is the name of the theorem. Okay, and I don't know if we have enough time to decode what that means. But simply speaking, if you have, let us say, a permutation, let us say 6 objects. Okay, so 1, 2, 3, 4, 5, 6, and let us say we permute them as 2, 1, 4, 5, 6, 3. Okay, and so typical way of expressing this as a function, right? So we define a permutation of, let us say, if I call this set as S, also a bijection, generally speaking. Or no, let me not put it that way. Just as a function. So F, which is going from okay. So basically, f of I refers to what is the number in ith position. Okay, so the number in ith position. Okay, in other words, what I've written here is I'm saying I could have, instead of drawing it this way, I could also written it like f of 1 is 2, f of 2 is 1, etc. 4, 5, 6. So the permutation is like applying a function to this set of numbers, and by design you can see that it's going to be a bijection because there's going to be one-to-one correspondence. And very often the symbol used to denote the permutation is sigma. So this sigma is a small s in Greek. Small s in Greek. Its capital sigma is this one is used for summation. This is the small sigma. So often we use the letter sigma. So typically you may see like even a permutation sigma. Like you may see this terminology in some textbook. Like for example, let I be the numbers 1 to 100. Let sigma 0. Okay, so this kind of notation you may often encounter. So when we say sigma I, sigma sigma of n refers to the number in the nth position. A typical notation. Any symbol doesn't matter really. So the fact that it's a bijection has some consequences. So the first thing is that a bijection has an inverse, right? So if there is a function which maps from the first set to the second one, there also has to be an inverse function which maps from the second one to the first one. So for example, in this case, if you see, if f of 1 is 2, then f inverse of 2 has to be 1. Okay. And similarly, like if I go down the list, f inverse of 1 has to be 2. F inverse of 4 has to be 3. F inverse of 5 has to be 4. F inverse of 6 has to be 5. Okay, so here I've constructed the inverse function of my function. Okay. And like if you draw a function like a diagram, you're just reversing the direction of all the arrows, right? The arrow, instead of going from left to right, is going from right to left. But I mean, in terms of permutation, if you see what this inverse function is telling about the original mapping. Basically, f of I answers the question, what is the element in position number I? And whereas the inverse function is giving the answer, where should we place I? Okay. So for example, if inverse of 5 is 4 is saying that put 5 in the fourth position. Like that. Okay. So it is asking finally both of them are going to give you the complete permutation, but we are reversing the matters. In the first case, we are first choosing the position, and then we are saying which element I should put there. In the second case, I'm starting with the element, and then I'm asking where should I place this element. Okay, so there's slight change in the order of things. Okay. Along with this, functions, bijections also have one more property, that you can apply them repeatedly because they are going from the same set to the same set. I can keep doing that, right? Again and again. Every time I can apply the same. So I can ask the question, what is f of I? That is applying the same permutation 2 times, okay? Or often it is denoted as f square of I, okay? So applying the same permutation 2 times. And like just to show an example that how will this permutation change under this operation. So one. Okay, so how do you construct? So this was the original sequence. This is f of I, and now I'm interested in f square of I. So how do we construct that? So observe what happened to the original sequence and do the same thing to this. So for example, in this case, these two got exchanged. 3 went here, 4 went here. 5 went here. So if I do the same operation here, so I'll first exchange these two, right? Then 4 will go here. So 5 will come here. 6 will come here. Okay, I hope you are following how we have constructed f square of the function applied 2 times. And do you notice anything about this operation? That what it has done? Firstly, the original 2 items have come back. Like 1, 2 started, became 2, 1, and it is back to 1, 2. And 3, 4, 5, 6, do you see in how many steps, if I keep doing this, that 3, 4, 5, 6 will also become normal, back to the original. If you think of it, it's actually just cyclic shift, right? These 4 elements are just rotating among themselves. Like the element at the start is going towards the end, and everything else is shifting to the left by 1 place, right? So how many times do I need to apply the function f, after which I'll get 3, 4, 5, 6 back again? 4 times, right? Because every time one position is shifting. So like without even calculating, can we be sure that what is f raised to 4i? F applied 4 times will be just 1, 2, 3, 4, 5, 6 again. Do you agree? And this is not a coincidence. I mean, it is not difficult to prove that every permutation will eventually come back to the original sequence. Can you think of the reason why that has to happen? Why, if you keep applying the same permutation again and again, sooner or later you are going to restore the original sequence. Yes. Okay, but you may get stuck in a loop, right? I mean, you start from some position, you reach somewhere, and then you keep repeating the same pattern. You never come back to the starting point. This could happen. Yeah, the point is valid that the number of permutations possible is finite. So sooner or later, you will run out of permutations. Like you will have to repeat some elements. But the question is why it has to come back to the original 1, 2, 3, 4, 5, 6. Maybe it gets stuck in some kind of a loop. So why cannot it get stuck in a loop like that? Those are online. Are you understanding the difficulty? That how should we prove that we are going to come back to the original 1, 2, 3, 4, 5? What will go wrong with this picture? Like what I'm showing here. Let me just draw it a little bit clearly. So let us just start from 1, 2, 3, 4, 5, 6. You reach some sequence, and then through some loop, you are going to come back to that original sequence, and you keep going in this direction forever. What is wrong with this picture? So the thing is, f is a bijection, right? And so f has an inverse. And does it have one inverse or two inverses? A bijection can only have one inverse, right? The inverse is unique. But in this picture, it looks like there are two elements which are both mapping to the same thing. So if I have to apply F inverse to this object, won't I land in a like ambiguity? Whether the inverse of this is this or this. There cannot be two answers that way. So that is why this picture does not look right. But how do we formalize this? Okay. Can we think of a way to write this more clearly? So let me first write the claim and then we'll try to formalize it. So let me do it in the form of a theorem. So let S be the set of numbers 1 to n for some natural number. Let sigma then my claim is then there exists some k such that sigma applied k times is the identity function. Okay. So there are several ways to write it. Like I could say sigma raised to k is the identity function. I could say that sigma k of I is I for all I. Or I could simply say that sigma raised to k is equal to, I think there's some special symbol that is used, like in is used to denote the identity function from a set to itself. But either way, the what we are saying is the same thing, that after some number of times applying the same function again and again, we are going to get the identity permutation. Because understand, doing nothing is also permutation, right? If I keep 1, 2, 3, 4, 5, 6 intact, right, where they are, that is also a valid permutation. So what we are saying is that the operation of applying the sigma k times is equivalent to that identity permutation. Okay. And so what we know is that sigma is a bijection. The permutation means that it is a bijection. So proof. So consider the set of all permutations. There may be some special symbol for that, but I don't know right now. So let me just use this fancy P. So how many elements does this capital P have? Every possible permutation is a member of this. So n factorial. So NP, the number of elements in P is n factorial. Understand that the elements of P are functions. Each element of P is a permutation, but as we, in our terminology, now that is a function. Okay. And so this sigma is also a part. So even sigma is the element of P, right? And now we are considering consider sigma, sigma square, sigma cube. This infinite family. By the way, I made a mistake here. This should be k greater than 0. Because if I set k equal to 0, then sigma raised to 0 is the operation of doing nothing. That is the identity. It's like in indices, like a raised to 0 is 1, right? So I'm strictly starting from sigma raised to 1 and going like this. And as what you already pointed out, that because the number of elements in P is finite, this sequence has to repeat at some point, right? So in this sequence has to repeat. But we don't know where it starts to repeat. So let us be generous and let us say, let you can choose any, like let K and L smallest what's that, and let us say K is smaller than L. Okay, so that sigma is to K is equal to sigma raised to L. So going back to the picture, what is the picture I'm drawing is that this is my sigma 1, sigma 2, this is sigma k, and from sigma k we are looping, and after a few steps we are coming back to sigma raised to L, which is identical to sigma k. So this is the picture I'm drawing, that this sigma raised to k and sigma raised to L are identical. And so I have to show some contradiction here now, that k is less than L and this is happening. So first thing is that so what can I do? What if I apply sigma inverse to both terms? Okay, what will I get? Okay, here I'm introducing one notation called composition. So this small circle denotes combining two functions. Okay, so when I denote this, like if f and g are functions, then f, this is read as f composite g, is nothing but the new function which is considered by applying f followed by g to any element. Okay, so this is a new function which I'm creating by combining functions. Okay, you are going to see this notation often later on also. So, and there are some textbooks which try to use the opposite convention, that because if you think about it, here when you read from left to right, they said f composite g, but when you're applying, actually you're applying g first, and then the result of that you're applying f. So order in which you're applying is actually g followed by f, but when you're writing from left to right, it looks like f something g. But visually it looks correct, right? If we are going from left to right, let us go from left to right. But some textbooks may like to flip it around. But anyway, we'll keep it this way. So if I apply the same sigma inverse to both of these, right? So I'm going to get sigma raised to k minus 1 is equal to sigma raised to n minus 1. And that is the contradiction. Because I had chosen k and l to be the smallest elements, right? And now I'm getting two elements which are even smaller. So the only way to get out of this contradiction is that this the only way out is that this k is equal to 0. Okay, so therefore the actual picture looks like this, that you start from sigma 1, you reach some sigma k, but that sigma k turns out to be sigma 0. Sigma 0, or sorry, I want to say sigma raised to. Okay, so sigma raised to 0, which is the identity. So the only way that can be completed is that we are going to go in a loop, but that loop involves sigma raised to 0 also, which is the identity point. Okay, so there could be a slightly better way of writing this, but for now, let us keep it this way. So the only case where from k I cannot descend to k minus 1 is when k itself is 0. Anything which is greater than 0, I can always do this. Therefore, sigma raised to- Okay, so are you able to follow the proof online? I mean, visually the picture was clear previously also that one point cannot have two inverses, but how do you formalize the idea that one point cannot have two inverses? So this is the way that let these 2 points be identical, then we apply the inverse to both of them, and you get one more point. So in other words, in if we go back to the picture, what we are kind of saying is that if this is the diagram where we are coming back to the same point, then by virtue of the fact that there is a unique inverse, the point just before this, right? So if I mark them as crosses, they also have to be equal. If this point is the same, then there are like what they're called pre-permutation, like the place from where you came from, these two also have to be equal. And you can keep going back to the chain, right? So if these two have to be equal, then these two also have to be equal, and like that. So this entire branch has to coincide with this one. It cannot be a separate thread that. Okay, that was the picture. Because this is the identity permutation. And the fact that every permutation eventually comes back to the starting point, there is one more way of capturing that, and that is representing the permutation as cycle. Okay? So the idea is, I'll show a different way of denoting the permutation. So denoting permutation as cycle. Okay? So like previously we denoted the permutation as a function. That function like 1 goes to 2, 2 goes to 1. But this is a much more compact notation that we are going to look at. So using the same example again. Right? So this was the permutation. So what I do, I denote it as brackets. So in the first bracket, I start with the first element. Okay, 1. Where does 1 go in this process? So 1 goes to 2. Where does 2 go? 2 goes back to 1. And so instead of writing 1 again, I just close the bracket. So this denotes the fact that 1 goes to 2 and 2 comes back to 1. So this is the cycle. Okay. So just a compact way of writing that f of 1 is 2 and f of 2 is 1. Then I proceed to the next element. So 3. Where does 3 go? So now there are two ways of writing it. Right? So we denote. Let us denote the positions. That okay, which position does 3 go to? So 3 goes to the last position, so the 6th position, right? And then 6 goes to the 3rd position. No, I think this is not the permutation that we took earlier, right? What was that permutation? Can you tell me? 4, 5, 6. Okay. Okay. Let me just write this again. So now 3 goes to the 6th position, right? But then let's do it this way, that wherever 3 was, we are replacing it by 4 in this process. So like that. So in the 3rd place, 4 is coming now. Okay. Then wherever 4 is there, we are replacing that by 5. Right. Then wherever 5 is there, we are replacing that by 6. And wherever 6 is there, we are replacing that by 3. And again, I will not write 3, I'll just close the bracket. Okay, so this is a compact way of showing the same permutation. So I can write sigma is equal to this. Okay. So looking at this, I understand that 3 goes to 4, 4 goes to 5, 5 is 5. Okay. So f of 3 is 4, f of 4 is 5. So this emphasizes the idea that a permutation can be split into cycles. So each of these is called a cycle. Okay. So this kind of notation, like some elements, is called a cycle. Okay. So any example you can decompose into these cycles. And if you notice that uh, what is the smallest k for which the whole permutation will come back to identity? Can anybody answer this question? What is that value k? Like in our example, that was 4, right? After applying the permutation 4 times, we came back to the identity. But in general, for any permutation, suppose you have decomposed that into these cycles, then can we say that after how many iterations we are going to come back to the identity? So let us say, for example, I have cycle 1 of length L1, cycle 2 of length L2, and cycle R of length LR. So let us say my permutation is decomposed into these R cycles. Then see, each cycle will have its own periodicity, right? So cycle of length 2 will return to the normalcy after 2 permutations, and the 4 one will happen after 4. So then at what point will all of them come back? Only then the whole permutation will be restored, right? LCM. Okay. Do you agree that if I take the LCM of all of these lengths, then at that point, all the cycles will have restored to the original state. And at that point, the whole permutation will be back to identity. Okay. Let me just give 1 or 2 more examples of this, like how to decompose a permutation into cycles. Let me just take another example. So let us continue with 6 elements only. And let me write it vertically. Okay, so this is a function. So you can think of this is I and this is sigma of I. So sigma of 1 is 2, sigma of 2 is 4, etc. etc. So how will you denote this in terms of the cycle notation? So can I write this as? So 1 is going to 2. So I'll start my bracket. 2 goes to 4. 4 goes to 5. And 5 comes back to 1. So this is my first bracket. And you'll notice that 3 and 6 remain in place. So you can just denote, you can skip them also because if you think about it, this cycle represents a permutation, like an operation that you have to apply to these numbers. If you just apply this much, it is sufficient. Like 3 and 6 won't change. But just for sake of completion, you can write them as single 3 and 6. But it is optional. Okay. So here 3 and 6 are called fixed points. Okay. Of this permutation. Okay. So any permutation can have all the points can be fixed. If it's identity, then every point is a fixed point. And in the other case, there's something called derangement. Have you heard of this term? So derangement is a permutation which has no fixed points. So in that, every term goes to a different term compulsory. Like this one was the derangement. Okay. So the term is derangement. Like arrangement. Derangement is a permutation with no fixed point. And we know that the total number of permutations is n factorial, but the total number of derangements for n objects, like how do we count those derangements? That is a standard problem in inclusion exclusion principle. So have you studied inclusion exclusion? then you can try this problem. In fact, let us try it now. Okay. So the question is, count the number. It's a slight detour from the permutation theory, but anyway, let's do it. So number n. Okay, and typically it is denoted by capital Dn. Okay, so capital Dn denotes the number of derangements of n objects. Okay, online, are you following? What is the meaning of a derangement? It is just an arrangement where no point remains fixed. Every point has to go to a different location. Can you raise your hand if you already know how to find this formula? Okay, nobody has done it. But is everybody aware of inclusion-exclusion principle? Okay, 3, 4, 4. Because you need inclusion-exclusion to do this problem. Okay, 4 or 5 of you know. So just to get you started, that to apply inclusion-exclusion principle, we need to define the set, right? Like number of sets which each of them have some property, and then we are interested in counting the union or intersection or those kind of things. And here the property we are trying to find is that, like, we want arrangements which have no fixed points. So, like, can we define the set in terms of whether each element is a fixed point or not a fixed point? So maybe you can consider one set of all the permutations where the first element is a fixed point, where the second element is a fixed point, and like that up to the nth element. Okay. So I'm suggesting that let the set AI be the set of all permutations of length n. I won't write that every time. Such that now there are two ways to define. I could either define the set as all the ones where I is not a fixed point or is a fixed point. But as it turns out, it is easier to measure when I say that I is a fixed point. Okay. And then we'll count the complement because we are interested in the set where there are no fixed points. So this AI, so I going from 1 to n, these n sets I'm going to define. Okay. Like in terms of Venn diagram, it will look something like this, right? This is the universal set of all my permutations, and this is AI, A1, A2, etc. Okay. And now which region am I interested in counting? Because I don't want even a single fixed point, right? So everything which is outside all this. So I'm interested in counting this region, which is outside all my set. So what I can do, I can count the union of my A1, A2, A3 and I take its complement, because I know the whole set has n factorial elements. So if I just count the union and subtract n factorial, that from n factorial, I'll get the answer. So I need to find the number of elements in the union. Okay. And so what is the Pigeon inclusion exclusion principle? What do I need to count in order to count this? Correct. Correct. The 2 at a time, then plus 3 at a time. So like that alternate addition and subtraction I have to do, right? So if I just denote it here. So this will be equal to sum of model of AI. So all 1 at a time minus sum of modular AI intersection agent. So where I and here I'm not writing this thing every time, etc. And in general, what will be the case term? Like if I'm going to take AI1, AI2 up to AIK. Okay? So I'm going to take the intersection of K set and there's the sum. And what will be the sign here? It will be minus 1 raised to K plus 1, right? So this kind of sum I'm interested in. And like the final term will be the intersection of all of them, right? A1 to AN. And for that, the sign will be minus 1 raised to N plus 2. So in general, if I can count this element, then the same formula will be applicable everywhere. So what does this intersection represent? Where AI1, AI2, AIK, we are all intersecting all of them. So in terms of what is the property of that permutation? Yeah, all of these are fixed points. I1 will remain in its own place, I2 will remain in its own place, and IK will remain in its own place. But everything else is free to get permuted. So how many elements will this set have? N choose K into N minus K. So here I know, let us say I know I1, I2, IK. So choosing the I1, I2, IK, yeah, so that N choose K will be for the sigma, right? So just this absolute value will be N minus K factorial, correct? So like for a given AI1, AI2, AIK, so this will be equal to N minus K factorial because I'm just going to permute the remaining N minus K elements anyhow I want. There are no restrictions on those elements. So you see, that is the beauty of inclusion exclusion, that we don't care about, some of them may be fixed points, may not be fixed points in those N minus K, but we don't care about them because that double counting will be taken care of in the whole expression. The only thing we are fixing is that these I1, I2, IK are definitely fixed points. So this is the number of elements in this, and now as you said correctly, that this sigma will go over N choose K. So this whole term, entire term will become minus 1 raised to K plus 1 N choose K into N minus K factor. And so if you expand this, do you see that N minus K factor will cancel out? And so what will this become? Simply N factorial upon K factorial. And so all I have to do is take the sum of this as K varies from 1 to N. Right? And remember, this is the complement. So finally I have to subtract N factorial minus this. So putting everything together, I think we can directly write the final expression. Maybe those who are not able to keep up with the calculations, you can revisit this later, but it should be clear that what we are doing. So Dn is the entire original universal set, which is factorial minus this summation that we are talking about. So in that, the first element, like when I put k is equal to 1, what do I get? N factorial. Okay. I mean, this Dn doesn't have a very nice expression, and there is no way to simplify this. At most, you can take n factorial common out of everything, right? Like here also there's n factorial. So like in textbooks, you may typically find the expression is written as, they just take n factorial common, and you observe that because 0 factorial is also 1, right? So if I just denote 0 factorial here, then this whole thing will become n factorial times 1 upon 0 factorial minus 1 upon 1 factorial. So the general term is 1 raised to k, 1 upon k factorial. Okay. And you can cross check that this formula is true for a few small values. Okay. So the homework for you is, this was Dn. So Dn is the number of arrangements which have no fixed points, but I can modify the question slightly. I want exactly k fixed points. Okay. So count the number of permutations which have exactly, let's not use k because we have k everywhere, r maybe. So count the number of permutations, count d n, r, which is defined as the number of, of n objects. Exactly RP. Okay, so try this at home. And if what you're doing is correct, you should expect that d of n comma 0 will be identical to dn that we found. Because when I've set r equal to 0, it means that I'm just talking about derangements. And not only that, one more property should be satisfied, that if I add them all, right? So d of n comma 0 plus d of n comma 1 all the way to d of n comma n, what should this be equal to? N factorial, right? In factorial, right? Yeah, because every permutation has to be in one of the categories. Either it has 0 fixed points, 1 fixed point, or all the points are fixed. Obviously, this last term is trivially equal to 1 because there is only one permutation with only one fixed point. Okay. So, like whatever formula you get, cross check that these two are also true. Okay. And the approach is again inclusion exclusion principle only. Okay. But anyway, this was a slight deviation from the permutation topic. So apart from that cycles thing, one more property about permutation I want to point out. Then we can move on to the next problem. Do you know one very interesting place where this permutation, the fact that if you keep applying the permutation again and again, you'll come back to the original. Do you know where you can apply it? In Rubik's Cube. If you think about it, Rubik's Cube is nothing but permutation. Like if you take a Rubik's Cube and rotate any one piece or one face, you are just rearranging the cubes in different positions, right? And so just take any operation. Let us say I'm going to turn the right side and the top side. Okay, this I define as my permutation sigma. Okay, turn the right clockwise and turn the top clockwise. And just keep doing that mechanically. Again and again, same permutation. Eventually, you will come back to the starting position. If what we have studied is true, that should happen, right? So try this at home. If you have a Rubik's Cube, first you have to have a Rubik's Cube which is completely assembled. Otherwise, even if you come back to the starting position, you will not recognize it. So start with a fully solved Rubik's Cube and then apply any, and doesn't have to, it can be very complicated. Like it could be a 17 more combination of permutations, and that I'm calling sigma. And if you keep applying that sigma again and again, eventually you will come back to the solved Rubik's Cube. It's a fun exercise. It takes a lot of time. Sometimes it takes, and there is one combination, it takes 120 moves to come back. And you get obsessed. Like once you start doing it, you cannot stop. Until you come back to the starting point, you will keep trying it. But it is a fun activity. So yeah, just to highlight what I said earlier, that why permutations are so powerful. So let me just illustrate the fact that anything else that you can do, you can represent as a permutation. That is what I want to say. So, like, let us say, take the example of modulo arithmetic that we are all familiar with, right? So the operation of, let us say, operation of okay, so if I have any number x, okay, and so because I'm going to do everything modulo 7, let me consider my set, and this is often Z7. So that is the set of all the remainders which I'm going to get modulo 7. Okay, and so this let f denote this operation, the operation of multiplying by 3. So in other words, f of 0 is 0, f of 1 is 3, then f of 2 is 6. How much is f of 3? F is 9, but modulo 7, that is simply 2, right? F of 4 is 12, which is 5. f of 5, which is 3 times 5, 15, which is 1. And finally f of 6, which is 6 times 3 is 18, which is 4. Do you see that it's a permutation? This is a permutation. So in fact, this Z7, if I have to define multiplication on this, to define if I have to define the operation of multiplication on this Z7, I have to create what is called a multiplication table, where I need to explicitly write out what is the answer of every number multiplied by every other number. Okay, so that will be a giant 7 cross 7 multiplication table. Okay, so it will look something like this. I will not draw it here, but you will see this diagram in many textbooks. Okay, so where they have like columns here. So in the column you have 0, 1, 2, 3 up to 6, and your rows like 0, 1, 2, 3 up to 6. And so in each entry, you will write what is that particular product. So for example, here in this column, it will be 2 3s are 6 and 3 3s are 9, which is 2. And like that. So this whole table will be filled by every combination of product. And so what we are saying here is that, so here we have constructed the multiplication by 3. So in other words, we are only constructed this column, right? And that if I just write it here, so it is 0, 3, 6, 2, 5, 1, 4. And so the major observation is that every column is a permutation of these numbers. And so what the implication is that this entire, all the operations that you're doing on Z7, this and same for addition also, because in adding by 1, for example, is a permutation. It's actually a cyclic shift if you think about it. If I add 1, 0 goes to 1, 1 goes to 2, and 6 comes back to 0. So it's a cyclic shift. So both addition and multiplication on this Z7 are permutations. And so what we are essentially talking about is a permutation group. Okay, I don't know if you have been interested in that topic of groups, but at some point you will encounter this topic, so permutation group. Okay. So the operation of applying permutations one after the other can be thought of like multiplication. And so under that multiplication, every object has an inverse, and those associativity and all those properties are true. So let me find out the name of that. Okay, this for this. This ceremony. Okay. CAY-LGY theorem is that so we don't know what is the group, we don't know what is the meaning of isomorphic right now, but if this statement sounds interesting, then it is up to you to read more about it. And by the way, in yesterday's post, Kanav, we were also discussing, I used the same word isomorphism, if you remember. So what is this meaning of isomorphism? It's a very powerful concept of isomorphism. It's a, you can think of it as a bijection superpowers. See, bijection only says that every element of the first set goes to every element of the second set. Like there's a one-to-one correspondence. But isomorphism says that every operation performed in the same set also maps in the same way. So if I have two sets like this, right? Okay. And let us say this under, I already have a bijection, let's say, where this object is going to this object and some other object is going to other object. What isomorphism adds is that if I, let us say, add these two, right? So if I add A plus B to get C, then on this side also I can define some kind of addition where if I can add this capital A and capital P to get capital C, and these two are related under the same operation. So like addition can also be passed through the same function and you'll get addition on the other side. So that is what isomorphism means. And same for multiplication also. So what this Cayley's theorem says is that any group can be shown through some isomorphism to be a permutation group. And I just show the example here. In fact, kind of we already shown the proof of it here, that for this multiplication, we clearly see that multiplying by 3 itself is a permutation. And there is nothing special about 3. You can multiply by any element, you are going to get a permutation that way. Okay. But anyway, I mean, we are not in a position to formally develop these ideas. If you're interested, read more about it. Okay. We have 20 minutes left, so we can do one more question. Okay, let's do question 1, that XYZ. Has anybody solved that question? So given XYZ positive, yes, Rohan, you also solved it. Just a minute, let me check. Mhm. Mhm. Correct. Mhm. Yes. Mhm. Yeah, and it continues to remain plus. Yes, Rohan.
Yes, so tell the solution.
Yes, go ahead.
So 1 upon x is yz, and 1 upon x is yz, 1 upon y
Yes.
is so we can rewrite it like that.
Yes. So we'll get xy plus yz plus zx greater than x plus y plus z. Okay.
Yes, so now we take x plus y plus z to the other side and add and subtract 1.
Yes. Okay. And then we can factorize it, right?
Yes.
Okay. So what do we get?
So we
One
get,
minus.
yeah. And now whenever 1 minus x is positive,
Yeah. Okay. Yes. Go ahead.
whenever 1 minus x is positive, 1 minus x to the k is also positive.
Yes.
And
Correct.
whenever it is negative or 0, it is the 1 minus x to the k is also negative or 0. So 1 minus x to the k into 1 minus y to the k into 1 minus z to the k is also greater than or equal to 0.
Less than or equal to 0, right?
It's greater.
Oh, sorry. Yes. Basically, I mean, the condition of positive or negativity does not change. Like if a number is already greater than 1, its subsequent powers will continue to be greater than 1. And if a number is smaller than 1, then its subsequent powers will also be smaller than 1. So basically, we are using the fact that 1 minus x is greater than 0 if and only if 1 minus x raised to k is also greater than equal to 0. And same for all the other terms. So if you multiply it, all of it together, and basically, I mean, uh, at this point, we can be slightly careful that uh, like how many of these terms are allowed to be positive and negative. So we have some cases about that, but in every case, whatever happens to x, y, z will also happen to x raised to k, y raised to k, right?
Yes, sir.
Yes. Okay. One could also try some kind of induction, like basically the base case is already done, like k is equal to 1 is given. And suppose we assume the k situation, and from there we're trying to prove k plus 1. So I've not tried it actually, but I don't know if anybody has thought about this possibility that from the k, the statement about k, can we derive something about the k plus 1? So, I mean, I want to prove that the statement about x is to k plus 1 is true, starting from the one about k. So I'll certainly get the term right, but I also want to get some extra cost, right? To understand it, not right? If I can show that what I'm adding here is much larger than the one, then I can subtract. It's just that this term, are you following this approach? Online that if I can show that this extra term on the right side is greater than the extra term which is there on the left side, then I can, uh, if this is true, then I can multiply both with a minus sign and I will get, and then I can add this to the original so that will cancel out the extra. So for that, I need to prove this. But I don't know if this works. Firstly, it is a symmetric sum, so there are six elements, not three. Maybe I will try smaller elements. Okay, I mean the problem is simple enough that you don't need to apply anything different. Any other approach to this question? Other than what you did? If not in the remaining question about 10 plus 3 and n square plus 3 is perfectly. So I think the essential idea at least is I have to follow the estimate, right? Whenever you have, if m is the perfect cube, then obviously n square is also perfect cube. Like, if n plus 3 is the perfect cube, then n plus 3 bracket square is also perfect cube. And you cannot have two perfect cubes very close to each other. So that is what I could use. I try to see what is the but this is okay. So if we just multiply these together, turns out that is so obviously the product is also your perfect. And that is n plus 2 bits. So what you have is to consider the first two and that is down. How do you think about that? The traditional approach that I followed is based on downward calculations. I don't know, is that if, as I said, that n plus 3 is a perfect cube, so naturally my kind of thinking of at least square that. So square plus 6 and plus 9 is also perfect. And so if these two are perfect cubes, they cannot be that close to each other. I use some kind of estimation to show that. So basically what happens is that if I say that this is equal to a cube, then now this is a square cube of a. And so if this is smaller than that, so actually I have to make cases because I will not even integers such as negative also. But for now dealing with the positive case, so I evaluated what is the previous cube that is from before that, a square minus a, and I can compare and show that I mean this has to be equal to this. There is no other choice because there is not enough gas. So then that is contrary. But anybody else online who observed this trick of multiplying the two together? And how do you design a question like this? Multiplying. In hindsight, now I see how because if I just notice as m plus 2 plus 1, now this is the standard factorization. So from here I can see how you can go. That is they started with this expression, then they factored it in this way, and now they're saying that this can make up. minus x plus b is a plus b x square minus a equal. Okay, that is also. Because when I factor it, yeah, I don't have anything else to add. It's just only to approach it that. So I only one approach, but this one also. So difficulty with the solution. But why do you feel like you how you get so every week I think so we'll do some problems and along with that whatever care is required we'll get that. And particularly for cognitive it's also important for you to write some solutions. Right? It's not enough to just discuss them in class, but how you present them is also important. So I would suggest that whatever problem is pending you, if you solve them, you can write and send your solutions to me. Or maybe post it on the group also. That's fine. So I can post that and give you some feedback. Are you is a better way to write it? Right. That's all. You want to talk about that concept of rational numbers, which is trying real numbers, but that is also a interesting separate topic. Okay, that's all. Thank you. Oh, actually, I removed my earphones. Were you able to hear me online? I thought.
Yes.
Okay, fine. I completely forgot that I connected the headphones. Okay, bye.